In this lecture, we will talk about some of the basic properties of the nucleus. So, there will be two parts to it. The next one will be, I will discuss some of the things which I will not have discussed here. Okay. So, overall, I will talk about the constituents of the nucleus, neutron, proton mainly, but also there are virtual particles like delta, resonance and pion and rho and omega mesons and so on. Then I will talk about the size of the nucleus and how that is determined. Then the electric charge, and as I said in part 2, I will talk about the spatial distribution of the electric charge in the nucleus. Then we will talk about conserved quantities, so called, which lead to good quantum numbers, namely energy of the nucleus. We talk about this in terms of the excitation energy. So, there is a ground state and there are various excited states of the nucleus. Then there is the angular momentum of a nucleus. It can have angular momentum which is finite. Then there is the parity of the states in the nucleus. It can be plus, positive or negative. Isospin of the nucleus, which is denoted by T, and some other quantities as well, but we will restrict ourselves to these conserved quantities. Then we will talk about the stability of the nucleus towards decay, and then of course, there comes the concept of lifetime of the nucleus. We will talk about various modes of decay, I just mentioned them of course. The gamma ray decay, conversion electron decay, decay by emission of neutrons, protons, alpha and fission fragments, then beta plus, minus, electron capture and so on. Okay. So, the constituents of the nucleus, the primary constituents are just protons and neutrons. There are Z protons and N neutrons. This is what we have learned over the last century or so. This is inferred from the measurements of its mass, electric charge and their distributions. We also have reactions such as EE prime P. So, you can knock out constituents of the nucleus using a high energy probe. EE prime N and photon induced reactions, photonuclear reactions, gamma P, gamma N and so on. We also infer such things from the spontaneous proton emission from certain proton rich nuclei such as 45 iron. So, if you get a proton coming out of a nucleus, we expect that it should be there also in the nucleus. And also we look at, among other things, neutron and proton emission from nuclei which are excited to energies beyond the separation energy of the neutron and proton in a nucleus. There is a smaller number of course, virtual particles. So, they are created and then they are destroyed in the nucleus as is allowed by the uncertainty principle. So, if you have a virtual particle like the pion, then it has a certain mass, then of course, it can only propagate for a distance corresponding to of the order of c times delta t, where delta t is just part of the relation delta E delta t of the order of h cross, the Heisenberg uncertainty principle. Similarly, if you have the rho and omega vector mesons, then of course, they can also be produced virtually. Of course, they travel shorter distances. So, in fact, we believe that the pion contributes to the long range part of the nucleon-nucleon interaction, whereas the rho and omega contribute to the short range part of the nucleon-nucleon interaction. There are also clusters of particles such as the alpha particle. The alpha consists of 2 protons and 2 neutrons, and it can happen that these 4 nucleons come together, they form an alpha, but then of course, it dissolves in the nucleus due to interactions within the nucleus. And we see of course, alpha particles in alpha decay, and so we believe that for some fraction of the time, these actually do exist in a nucleus which is alpha decaying. Okay, we come to the size of the nucleus. As we all know, the fact that the atom has a very tiny nucleus residing in it, about 10,000 times or so smaller than the atom itself or the size of the atom itself, that is inferred by Rutherford in his experiments with Geiger, Marsden and so on. And for instance, the classic case is one of alpha on gold scattering, where you saw the alpha particle getting scattered at backward angles, which should not have been the case had the nuclear size been larger. So, from these experiments, it was inferred that the nuclear size is smaller than about 50 Fermi or so, because The alpha particle that was used was from the spontaneous alpha decay of 226 radium, and that has an energy of about 5 MeV or so. So, you can compute the Coulomb energy at the distance of at the smallest distance that the alpha and nucleus can approach, and you will find that that is of this order of distance. So, it is smaller than 50 Fermi, but with the probes that Rutherford had at his disposal, one could not say whether it was much smaller than 50 or and so on. Electron scattering experiments, of course, with which use high energy electrons such that the de Broglie wavelength is of the order of a Fermi or so, they can be used, of course, for measuring the electric charge radius. And indeed, for momentum transfers which are of the order of the inverse of the momentum transfer is smaller than the radius of the nucleus, then of course you can even infer about the electric charge distribution in the nucleus. The other probe that we have is one of muonic atoms. Of course, you do not get a charge distribution there. You see isotopic shifts, or you see shifts in the energies of the 1s state of these muonic atoms. So, the muonic atom is basically one in which you have a mu minus coming close to the nucleus, and because it is about 200 times heavier than the electron, the 1s orbital radius in a muonic atom is of the order of 200 times smaller than that of the k electron in that atom. One can also measure isotope shifts using precision atomic laser spectroscopy, and finally one can do a hadron scattering, protons, pions and so on, to get the matter distribution and the radius. So, initially the radius, and then of course, if you have probes which penetrate a little more, then you can get the matter distribution as well. Okay, so just to show you a representative example of electron scattering experiment. This is from a paper in 1967, rather old, but it illustrates the fact that when you do electron scattering on a nucleus such as 40 calcium or 48 calcium, then you get a differential cross section d sigma by d omega, which comes down with theta. Now, theta can be translated into the momentum transfer. So, the higher the momentum transfer, the smaller the cross section, and we will see how that goes. What is the dependence on the momentum transfer? So, for 40 calcium, it is this. You can see that the experiment has measured this quantity over several orders of magnitude. So, it starts out with a few times 10 to the minus 28 centimeter square. Okay, that is like 100 of the order of 100 microbarn per steradian, and then it goes all the way down to 10 to the minus a few times, maybe 10 to the minus or of the order of 10 to the minus 34, which is like about 100 picobarns. So, from 100 microbarns you have gone to 100 picobarns. So, that is about 6 orders of magnitude, and similar is the case for 48 calcium. You can see that there is a slight shift in the minima, and it actually moves towards smaller angles, which means that the size of 48 calcium is slightly more than 40 calcium. Now, of course, you are measuring the charge distribution, and what is changing here is the neutron distribution. But if there are more neutrons on the outside of 48 calcium, they also tend to pull the protons along with them. So, because of the NP interaction, and so there is a slight difference in the charge radius as well of the 48 calcium as compared to 40 calcium. Okay, so now this was actually pioneered by Robert Hofstadter, who eventually got the Nobel Prize in 61 or 62, and he measured the electric charge distributions for various nuclei, right from light nuclei such as helium-4 right up to lead. Okay. So, you can see that if you plot the electric charge density in units of electronic charge per Fermi cubed, this peaks at 0 r equal to 0 and then falls off. Now, as you go to heavier and heavier nuclei, slowly the place where there is a fall off, let us say where it becomes half of its sort of roughly saturation value of the charge density, that slowly increases. Okay. And in fact, that can be parameterized. So, the charge radius goes as something like r 0 to the power into a to the power of 1/3, where a is the mass number of the nucleus and this is just n plus z, the number of neutrons plus the number of protons, which is for most stable nuclei varying between about half to about something like, so the z by a ratio is varying from about half to about 0.4 or so. Okay. But the radius is, as I said, the charge radius is going like r 0 times a to the 1/3 and r 0 is of the order of about 1.2 Fermi. So, you can see that if I have a equal to, let us say 216, then this is 6. So, this is about 7 Fermi. Okay. So, lead is close to 216, is actually there is a series of isotopes 204 to 208, but you can see that the half radius is of the order of 7 Fermi or so. This of course relationship holds for nuclei not too far from the line of stability, and we will come to that. So, you can have other probes, as I mentioned there, you can have hadronic probes, and the pi plus pi minus, they are both hadrons, they are mesons of course, and they interact strongly with nucleons. So, if you for instance look at the data that exists, then as a function of the total energy, you have a resonance at about 1.2 GeV. It is taken from some reference, Ericsson and somebody else. That is why this is EW, this has no other significance. And this is the cross section, the total cross section in millibars. So, you can see that if you with the pi plus p, this is a t equal to 1 system, p proton is t equal to half. So, you can Tz is equal to 3 halves. So, you can get a t equal to 3 half entity, and this happens to be the delta plus plus. This is the delta resonance, which has a mass of about 1.2 GeV, that is here. Okay. Now, you can also excite that with the pi minus on a proton, and this is of course a t equal to Tz equal to half state, and this is the, so since these two electric charges are opposite, you excite the delta 0 resonance. It is at almost the same energy as far as you can tell, and so this is also at the same place. So, the total cross section is about 3 times the delta with the pi plus p case as compared to the pi minus pk, but the elastic cross section, which of course I have not shown here, is about 9 times higher, and that actually comes about from the Clebsch-Gordon algebra, Clebsch-Gordon coefficients for the isospin. So, it turns out that you can easily understand that the elastic cross section at the peak or the delta resonance peak in the case of pi minus plus neutron is about 9 times the elastic cross section pi minus p, and similarly pi plus p is about 9 times pi plus n. Okay. So, in the case of the pi minus n, therefore, such a scattering process will be sensitive to the neutron skin of the nucleus. So, that is shown in this experimental plot taken from this reference in 77. This is a plot of the pi minus and the pi plus elastic scattering cross sections on 40 calcium and 48 calcium. As you can see, the 48 calcium has 8 more neutrons than 40 calcium, and they are the outermost neutrons. So, if you are sitting on the delta resonance, then the pi minus cross section should show an enhancement as compared to the pi plus cross section. Okay. So, this is what is shown here. The pi minus is this, these open circles, and the pi plus on the nucleus is these filled dots, you can see that there is a difference in this cross section. And of course, there are other protons and neutrons as well. So, it is not that you have only those outermost neutrons scattering. So, in any case, you can see that there is a difference in the cross section as a function of angle, and this is because pi minus is more sensitive to the neutrons at the delta resonance as compared to the protons. This is the angular distribution for calcium 40, and again there is a small neutron skin effect, which is why the pi minus calcium 40 elastic cross section is somewhat more than the pi plus elastic scattering cross section. So, this experiment actually found what is the difference between the effective root mean square radius for the pi plus, actually more sensitive to the skin, the outer part, because of course, this pion interacts strongly with the nucleus, so it is absorbed rather quickly. You cannot probe very much the interior. So, in any case, this difference R, the radius, root mean square radius is found from the pi minus scattering to pi plus scattering. If you take this difference, it is of the order of 0.21 Fermi in the case of calcium 40, but it is of the order of 0.5 Fermi in the case of 48 calcium. So, almost like 0.3 Fermi more in the case of 48 calcium. So, as you can see, you can use such probes to kind of be sensitive to the neutron, or in this case is the neutron, but if you were to use the pi plus and you have a proton rich nucleus, you can probe the proton skin as well. Okay. Now, we come to the another property of the nucleus, which is the electric charge. So, the electric charge is of course decided by the number of protons that exist there. So, it is plus Ze. So, elements 1 to 42, 44 to 83, and then 90 and 92 occur naturally, okay, they are stable. However, technetium, which is 43, that is unstable. So, we do not have this naturally occurring, but it can be produced through artificial means, and indeed this has been produced. And so also things like polonium, protactinium and so on, are astatine, radon, actinium, then radium and so on. Now, if you looked at even electron scattering, the scattering cross section at a momentum transfer equal to 0, that is actually proportional to Z squared. So, this is an independent way of measuring the, of course, probably you might say a more expensive way of measuring the charge on the nucleus, because when you do electron scattering, you can get much more information. But in any case, it is just nice to point out that at 0 momentum transfer, so from the uncertainty principle, this corresponds to large distances, you will see the nucleus as an entity which has a charge of plus Ze. Now, the mass of the nucleus is A times MAMU, or I mean, this is roughly speaking, but the binding energy of the nucleus is, if it is given by BE, then the mass is actually given by Z times the mass of the proton plus N times the mass of the neutron minus the binding energy. As we will see, this binding energy is somewhat less than a percent of each of these masses for of the proton and neutron. Now, the mass is measured using electric field, magnetic field combinations in so-called mass spectrometers, and they typically have a resolution of 10 to the minus 6. So, if you have, let us say, a mass 100 nucleus, then this quantity will be of the order of about 100 GeV. So, that is like 10 to the 11 electron volt, and if you have this kind of resolution, you get 10 to the 5 eV, which means of the order of 100 keV. Okay. So, the electric field actually bends it in a trajectory which is whose radius is proportional to the kinetic energy divided by Q times the electric field of an ion of mass m, which is going through this spectrometer, whereas the radius of curvature when the same ion is going through a magnetic field is proportional to P by QB. Okay. Now, of course, modern determinations do not use just these single or double focusing mass spectrometers. They actually use Penning traps or Paul traps, and these have a mass resolution which is much better. For stable ions, for instance, this is of the order of 10 to the minus 11. Okay. So, you can actually even measure the energy differences between isomeric states of the order of tens of keV away from the ground state. The principle in a Penning trap is just that you have you use the cyclotron principle. That means, if you have a magnetic field, then the mass is just given by the charge times the magnetic field magnitude divided by the cyclotron frequency, the angular frequency. And as I said already, the masses of isomeric excited nuclei also have been measured this way. This is particularly useful also if you have very short-lived isotopes, when it becomes inconvenient to actually make a put it in an ion source and then do the mass measurement in a traditional mass spectrometer. So, here you use very cute techniques like trapping the atom and then pushing it into a Penning trap and making it stay there till the time it decays. Okay. So, the shortest time lifetime entities, nuclei that have been measured is of the order of, I think, 100 milliseconds or thereabouts. So, this is what you can do in a Penning trap. There are other ways of measuring the masses of unstable species, and this is done in storage rings, where you produce this unstable species, you cool it very fast much before it decays using electron beam cooling, and then this cooled beam is circulated in a storage ring, sometimes after acceleration, or this has been done in, for instance, the GSI lab in Germany, and there you can get mass resolutions of the order of 10 to the minus 6. But here you can actually do this for, again, things which are even the lifetimes of the order of 100 microseconds. Okay. In principle. Okay, so this is a picture of a doubly focusing mass spectrometer. So, you have an ion source, and then you have an electric field, and you have a separated magnetic field. So, you analyze in terms of kinetic energy by Q, and then you analyze in terms of momentum by Q, and with this you can by shaping the edges of the magnet suitably, you can have a double focused beam, and then you have a detector doing that. And so, you can scan the magnetic field and so on, and then you can get a scan of the mass. Okay. So, this shows you how precision measurements have been made using two kinds of traps. So, one uses the magnetic field to and the cyclotron frequency, whereas the other technique, the Paul trap technique, does not use a magnetic field at all. So, let us come to the Penning trap. So, there what happens is that you have a cyclotron frequency which is like this. You put the ion whose mass you want to measure into a electrode geometry like this. You have a magnetic field which is going up vertically, and then you have these electrodes to which you apply voltages of the order of 10, 20 volts and so on, and they have a hyperbolic shape. So, the field is actually not allowing it to go in the z direction. However, in the x and y directions it can leak out. However, because of the magnetic field, it stays trapped in here. So, in principle you have three motions coming in. You have the cyclotron motion, which is this denoted by this circle here, and then you have a bigger circle denoted by the magnetron motion, and then the axial oscillation is given by, because axial oscillation, because both of these are at positive voltage. So, if an ion tries to go up, it is repelled, it comes back, and that is how it oscillates in the vertical direction. That is this vertical kind of oscillation. So, The electrostatic oscillation frequency in the z direction is given by this quantity, the charge times the DC voltage that you apply on these hyperbolic electrodes divided by md squared. And in the radial plane, there are two frequencies that come about, which is this omega c prime, which is omega c by 2 plus square root of this entity. Of course, this entity, as you can see, is smaller than omega c by 2. So, of course, if omega z is small, then it almost adds up to the cyclotron frequency, whereas here it subtracts and you get something which is of the order of omega z. Okay. So, these are the two frequencies that you get, and this motion is of course sensed by a resonant circuit, and so the motion of this ion, which is oscillating in this manner, is sensed by a resonant circuit which is connected to this device, and you can actually get from that, from the Fourier analyzing this, you can get a mass spectrum, and then this mass is stable to you can get it accurate to about 10 to the minus 10, 11 for stable ions, and less so for unstable ions. In the case of the Paul trap, you have no magnetic field, but you apply RF in the x and y directions. So, you can have focusing in the let us say in the x direction and defocusing in the y, but then because of RF in the next cycle, it is the other way around, it is defocusing in x and focusing in y, and so on. So, you can trap this ion here, and then again you use the same principle of a pickup. This is sensed by a resonant circuit, and you can get the mass of the ion depending on what its resonant frequency is. So, this is the review article where these things are discussed. As I said, you can also have a beam circulating in a storage ring after it is produced and then cooled with electron beam cooling. We have talked about it a little bit, but just to remind you, if the beam spread is large and it is co-moving with a electron beam whose energy is very precisely known and the spread is extremely small, then the ions share energy with the electron beam, and the electron beam, so to speak, hots up, and the random energy in the beam is dissipated, it goes to the electrons, and then the electrons go out, but then you can, in the next pass, you can again have this very sharply energy focused beam interacting with the beam and so on. So, within some number of cycles, you can cool this beam, and then it can keep circulating here. Okay. And then you have pickup electrodes which can pick up the oscillation or the frequency with which it is moving around, and that depends of course on the mass. So, you can get a whole spectrum in the of intensity versus frequency, and corresponding to this you have various masses, and so if there is an unknown object, you can find its mass out. Okay. So, for instance, here what is listed, the dark ones are where the mass is unknown, the others where mass is unknown. So, you can also use it for self calibrating this the method that you have used for measuring the mass. So, this is illustrated here in the GSI measurement, as I said already, the frequency is related to the mass, but also you can see that for this nucleus 140 promethium 58 plus, as a function of time from 13 to 169 seconds, you can see that the intensity has come down. This is not because it has got lost because of interactions with the residual gas in the vacuum, because you can see 140 cerium is more or less the same intensity. So, this is because it has decayed in the meanwhile. So, the lifetime is of the order of, let us say, 100 seconds or so in this case. Okay. This is the reference for that. Okay. So, from all these mass measurements, you can actually extract the binding energy. You saw the mass is just equal to n times the mass of the neutron plus z times the mass of the proton. So, you subtract from that the mass that you measure, and the negative of that actually gives you the binding energy, because of course, the nucleus is having a mass which is less than the sum of its individual neutron and proton components. So, then you can plot it as a function of mass number, where you plot binding energy per nucleon, okay, in MeV. And you can see there is a rise from the deuteron to about iron, and then so the maximum is at around 8.5 MeV or so, and then there is a slow drop off of the binding energy. That is because now the Coulomb energy goes like Z squared, whereas the nuclear binding energy goes only like A because of the short range of the nuclear interaction, the strong nuclear force, but the Coulomb force is a long range force. So, of course, that goes like Z squared, and therefore, you get this drop off. So, you can see that around iron we have the most stable nuclei, and therefore, for instance, these nuclei can decay through various channels, and for instance, U-235 plus a neutron can fission, and then you produce some things which are having a slightly higher binding energy in the final state. So, that leads to a release of energy. Similarly, if I take a deuteron, two deuterons, then they can form a helium atom whose binding energy is larger. Okay, helium is somewhere here. Okay, so the difference in energy is released as fusion energy. So, in fact, this is the domain of fusion, and this is the domain of fission. The figure is taken from this reference. Okay. So, if you were to now see plot the proton number versus neutron number, and we find that there are less than about 300 stable nuclei, and however, models of the nucleus tell us that this whole region here, not just the yellow region, but also the green region, there should be nuclei. So, that number comes out to be of the order of 8,000 or so. Okay. So, we know only these nuclei in the yellow region. They are of course unstable, but there is a lot more to discover. That is the point of showing this slide, and you do not see things beyond this, because that is so called drip line. So, at this place, for instance, you have the neutron drip line, and at this place you have the proton drip line, because at this place the proton binding energy goes to 0, the last proton, and similarly the last neutron binding energy goes to 0 here. So, this is called the neutron drip line, this is the proton drip line. Okay. Now, the other quantum numbers are the angular momentum, parity. So, we normally designate nuclei with this J pi. So, J standing for the angular momentum, pi for the parity, isospin. Of course, there are other quantum numbers like baryon number, lepton flavor, and so on. Angular momentum, of course, strictly conserved. The sum of the initial angular momenta, vector angular momenta, should be equal to the final angular momenta. And the ground state spin is usually determined in various ways. For instance, by NMR, if the J is not non-zero, is not applicable. If J is 0, then of course the NMR spectrum cannot tell you anything about the spin. But you can also look at the hyperfine structure of atomic spectra and so on, and there you can infer whether it's a 0 spin, if it's if things are singlets, or if it's doublet or triplet, and so on. So, parity is conserved in strong electromagnetic interactions. The weak interaction only contributes small admixtures of the opposite parity, which are typically of the order of 10 to the minus 12 in probability, but even probably smaller depending on the case. Isospin again is conserved in strong interactions, but of course is violated by, let us say, the electromagnetic interaction, by the Coulomb interaction, for instance. Similarly, no B baryon number, lepton number violation has been found except in neutrino oscillations. Some of the properties of nucleons are listed here. So, the electric charge for neutron and proton, mass of the, so you can notice that the mass of the neutron is slightly more than that of the proton, and that in fact leads to a free neutron decaying to a proton and two more leptons. The magnetic moment is minus 1.913 for a neutron as with respect to its spin, and plus 2.793 in units of the magneton. So, this is co-directional with its spin, this is having the opposite direction. And so, I have two comments here. The mass difference delta NP is of the order of 1.4 MeV, and since the neutron decays with this half life, then if neutrons have to survive, they can only do so when they combine with protons in nuclei. Free neutrons will not live longer than this. So, similarly, the magnetic moments differ from the Dirac values, magnetic moments for neutrons and protons, which is for neutrons it should have been 0, and plus mu n for the case of protons, but they are quite large in fact. And this can be of course rationalized in the old Yukawa picture. That means a neutron virtually can go into a pi minus and p, and since the pi minus is a pseudoscalar, so you can have a L equal to 1 pi minus, and then you can figure out that it actually will lead to a magnetic moment which is opposite to its spin. Similarly, a proton, a bare proton or a Dirac proton, let us say, can virtually go into a pi plus and a Dirac neutron, and so the pi plus is the one which actually gives it a large magnetic moment. In this Yukawa picture, you can also see that qualitatively you should have a charge distribution in the neutron. It should have a plus sign at small r and a negative sign at large r. This is because of this virtual process which is always going on. Okay, the stability of course of a nucleus is decided. So, one can decide whether or not this will be stable against decaying into B and C if this mass difference is positive. So, then we call this mass difference or this energy difference mc squared, mac squared minus mb plus mc squared. This is the Q value of the reaction. This is just jargon which is often used in nuclear physics. This is basically the energy released in a process A going to B plus C. And you can also have gamma decay if you have an excited state of a nucleus. If you have beta decay, then the Q value for beta decay is given by the difference in the masses of the initial and final nuclei. And if you have positron decay, of course, then you can have there is a typo here, this should have been beta plus. Then it should be the difference should be even greater than 2 mc squared, mec squared. In alpha decay, again the initial final states, the mass difference is mi minus mf minus m alpha this time, and of course this is just a necessary condition, but how fast this process proceeds depends on the tunneling probability, and this actually goes up exponentially with the Q value of the reaction. So, even a 100 keV difference in the Q value, an increase in 100 keV can make a difference in the lifetimes of several orders of magnitude. Similarly, you can have spontaneous fissioning nuclei. One such example is 252 californium. It in fact has a fairly large branch for spontaneous fission as compared to the alpha branch. It's of the order of 1 in 25. So, bulk decay is of course by alpha emission, but you still have a few percent decay through spontaneous fission. So, this is often used as a spontaneous fission source. And there are other very rare processes that can happen in a nucleus. You can have carbon 14 emission, silicon 28 emission spontaneously from a nucleus, and this has of course been observed. And this is an example of that, carbon 14 emission from 225 actinium, which has a half life of about 10 days, but we have seen carbon 14 which is emitted with about 28.6 MeV. Of course, this data shows just a few counts here, a couple of counts, 2-3 counts, and these are all the references that have attacked this problem. The last one of course is not, I think it's in radium, again a heavy fragment emission from radium, some radium isotope. The partial half life is of the order of 10 to the 17 seconds. You can see that this is of the order of 10 to the 6 seconds. So, the branching ratio is of the order of 10 to the minus 10, 10 to the minus 11. Okay. It's a very small branching ratio, but nevertheless it is interesting to see that if something is allowed, it can actually happen. Okay. So, in summary, we have looked at some of the basic properties of nuclei, including mass measurements, binding energy curve, electric charge radii, and then the relationship between charge radius and A. We have also seen the conditions for nuclear decay and some of the prominent decay channels. Thank you.